Download this code from codegive.com, link in the description below. Finding buffer overflow vulnerabilities with fuzzing, Episode 4, Code Examples and Advanced Techniques. This tutorial, Finding Buffer Overflow Vulnerabilities with Fuzzing, Episode 4, Code Examples and Advanced Techniques, expands on previous episodes to provide practical code examples and delve into more advanced fuzzing techniques for uncovering buffer overflows. We'll cover crafting fuzzers, analyzing crash outputs, and mitigating common issues. Recap of previous episodes, briefly. Episode 1, Introduction to Fuzzing covered the basics of fuzzing, its importance in security testing, and the different types of fuzzing, mutation-based, generation-based, etc. Episode 2, Setting up a fuzzing environment showed how to set up a basic fuzzing environment using tools like AFL, American Fuzzy Lop, or libfuzzer, and discussed essential tools for debugging and analyzing crashes, GDB, valgrind. Episode 3, Basic Fuzzing Techniques and Common Vulnerabilities demonstrated basic fuzzing techniques and identified common vulnerabilities beyond buffer overflows, such as integer overflows and format string vulnerabilities. Episode 4, Code Examples and Advanced Techniques. This episode focuses on 1. Crafting targeted fuzzers moving beyond random input generation to create more intelligent fuzzers that target specific code areas and input formats. 2. Code examples with buffer overflows providing vulnerable C/C++ code examples with buffer overflows and demonstrating how fuzzing can find them. 3. Analyzing crash dumps and root cause analysis deep diving into crash analysis using debuggers and tools to identify the exact location and cause of the overflow. 4. Instrumentation techniques using sanitizers, address sanitizer, memory sanitizer, and code coverage analysis to enhance fuzzing effectiveness. 5. Dealing with complex input formats addressing the challenges of fuzzing applications that use complex input formats like network protocols or file formats. 6. Advanced fuzzing strategies introducing techniques such as grammar-based fuzzing, feedback-driven fuzzing, and hybrid fuzzing. 1. Crafting targeted fuzzers. Instead of just feeding random bytes, targeted fuzzers are designed to generate inputs that are more likely to trigger vulnerabilities. This involves understanding the target application's input format and data processing logic. Knowledge-based fuzzing this is informed by knowledge of the application, its libraries, and its input formats. Example, if you're fuzzing a PNG image parser, you'd want your fuzzer to generate mostly valid PNG headers and data structures with deliberate corruptions at specific locations. Example, fuzzing a simple configuration file parser. Let's say our application reads a configuration file in the following format. A random fuzzer might generate completely nonsensical input, quickly being rejected by the parser. A targeted fuzzer would focus on valid section headers, section_name. Key value pairs, key equals value. Varying the length of keys and values, particularly exceeding buffer sizes. Introducing special characters that might be mishandled, example new lines, null bytes, characters that could be interpreted as format string specifiers. 2. Code examples with buffer overflows. Here are several C/C++ code examples containing buffer overflows that can be discovered through fuzzing. Example 1, strcpy overflow vulnerability the strcpy function copies the entire argv1 string into buffer without checking its size. If argv1 is longer than buffer_size, 1 bytes, leaving space for the null terminator, a buffer overflow occurs. Fuzzing A simple fuzzer would generate strings of increasing length until the overflow is triggered. To compile GCCO strcpy underscore overflow strcpy underscore overflow.c. To run with fuzzer using AFL fuzz I input O output slash strcpy underscore overflow at replace input with a directory containing initial seed inputs. Even just an empty file output is where AFL will store the crashes and interesting test cases. At tells AFL where the input file will be passed as an argument. Example 2, gets overflow vulnerability the gets function reads a line from standard input into buffer without any bounds checking. This is a textbook buffer overflow. Gets is so dangerous it has been removed from the C standard library in later versions. Fuzzing any input longer than buffer underscore size, 1 bytes will trigger the overflow. To compile GCCO gets underscore overflow.c, you may get a warning about gets. Ignore it for this example. To run with fuzzer using AFL fuzz I input O output slash gets underscore overflow, AFL will automatically pipe input to stdin for this application. Example 3, sprintf overflow vulnerability even with tinprintf used to prevent format string overflow, there remains the possibility of sprintf writing beyond the bounds of buffer. Specifically, if argv1 is very long, the string that is constructed in fmt by tinprintf, and therefore copied to buffer by sprintf, may still be too large for buffer even with a properly sized fmt. Fuzzing a fuzzer needs to generate very long strings to overflow buffer after it has been processed and copied from fmt. To compile GCCO sprintf underscore overflow.c. To run with fuzzer using AFL fuzz I input O output slash sprintf underscore overflow at. Example 4, heap overflow, more complex. Vulnerability the strcpy to my underscore struct dash data is a heap buffer overflow. If the input string argv1 is larger than the initially allocated data underscore size, strcpy will write beyond the allocated memory on the heap, potentially corrupting adjacent heap structures. This can lead to program crashes or, more severely, exploitation. Fuzzing the fuzzer needs to provide input strings longer than data underscore size to trigger the overflow. This is a more complex vulnerability because it affects the heap management. To compile GCCO heap underscore overflow.c. To run with fuzzer using AFL fuzz I input O output slash heap underscore overflow at. Important considerations for these examples input seeds start with simple input seeds. For strcpy underscore overflow, an empty file in the input directory is fine. AFL will mutate it. For the configuration file example, seed the input directory with a minimal, valid configuration file. *asan/msan compile with address sanitizer, asan, and memory sanitizer, msan, to help detect memory errors during fuzzing. Example, gcc sanitize equals address o strcpy underscore overflow strcpy underscore overflow.c. asan and msan provide detailed error reports when a memory corruption occurs, making debugging much easier. Error handling in a real-world application, there might be error handling that prevents the program from crashing outright due to the buffer overflow. The goal of fuzzing is to find these vulnerabilities before they can be exploited. Even if the program doesn't crash cleanly, ASAN or MSAN are likely to still detect the memory corruption. Varying buffer sizes. Experiment with different buffer sizes to understand how they affect the likelihood of finding a vulnerability. Smaller buffers are easier to overflow, but larger buffers can hide the problem, making it harder to detect with simple fuzzing. Compiler optimizations. Compiler optimizations can sometimes change the behavior of the program, making it harder or easier to trigger the vulnerability. Try compiling with different optimization levels, example 00, 01, 02, 03, to see how it affects the fuzzing results. 3. Analyzing crash dumps and root cause analysis. When a fuzzer finds a crash, it saves the input that triggered the crash. Analyzing these crashes is crucial to understanding the vulnerability. Using a debugger, GDB. 1. Run the program with the crashing input under GDB*. 2. Set a breakpoint, if needed. If you have a suspicion of where the crash is occurring, set a breakpoint using break_line_number or break function_name. 3. Run the program *run. 4. Examine the stack trace * when the program crashes, or hits a breakpoint, use the bt, backtrace, command to see the call stack. This shows you the sequence of function calls that led to the crash. 5. Examine variables * use print variable _name to inspect the values of variables at the point of the crash. This can help you understand how the overflow occurred. Using valgrind, MEMC-HEC. Valgrind's MEMC-HEC tool is excellent for detecting memory errors. 1. Run the program under valgrind *. 2. Analyze the output *. Valgrind will report any memory errors it detects, including invalid writes, which is what a buffer overflow causes. The output will provide information about the location of the error and the memory involved. Interpreting crash information segmentation fault, SIGSEG. This is a common signal indicating that the program tried to access memory it wasn't allowed to access. This is frequently caused by buffer overflows, null pointer dereference, and other memory corruption issues. Heap corruption. If you're fuzzing a heap-based vulnerability, the crash message might indicate heap corruption. This means that the heap metadata, used to manage memory allocations, has been overwritten, leading to unpredictable behavior. Address sanitizer, ASAN, output ASAN provides detailed error messages that point directly to the source of the memory corruption. It will tell you the type of error, example heap buffer overflow, stack buffer overflow, the address that was accessed, and the size of the access. Core dumps. Core dumps are snapshots of the program's memory at the time of the crash. They can be analyzed with GDB, but they can be very large. To enable core dumps, you might need to run ulimit unlimited. Example crash analysis with GDB, strcpy_overflow. 1. Compile *gcco strcpy_overflow strcpy_overflow.c. 2. Fuzz *afl fuzz I input o output /strcpy_overflow at let afl run for a bit until it finds a crash. 3. Identify crash input * find the crashing input file in the output/crashes directory, example output/crashes/id 000000 sig11 src. 4. Run with GDB *gdb/strcpy_overflow output/crashes/id 000000 sig11 src. 5. Run GDB *run. 6. Backtrace *bt. The backtrace will show that the crash occurred in the strcpy function, confirming the buffer overflow. Inspecting the buffer variable will show that it has been overwritten with the input data. 4. Instrumentation techniques. Instrumentation involves modifying the target program to collect more information during fuzzing. This information can be used to guide the fuzzer toward more interesting code paths and to detect vulnerabilities more effectively. Asterisk address sanitizer, ASAN. Asterisk purpose asterisk detects memory errors such as buffer overflows, use after free errors, and memory leaks. Asterisk how it works asterisk ASAN instruments the code to track memory allocations and accesses. It adds shadow memory alongside the allocated memory to track whether the memory is valid for reading or writing. Any out-of-bounds access is detected immediately. Asterisk how to use asterisk compile with fsanitize equals address. Example, gcc fsanitize equals address my_program.c. Asterisk benefits asterisk fast and precise error detection. Asterisk memory sanitizer, MSAN. Asterisk purpose asterisk detects reads of uninitialized memory. Asterisk how it works asterisk MSAN tracks whether memory has been initialized. Reading uninitialized memory can lead to unpredictable behavior and can sometimes be a security vulnerability. Asterisk how to use asterisk compile with fsanitize equals memory. Example, gcc fsanitize equals memory my_program.c. Asterisk benefits asterisk detects a class of vulnerabilities that ASAN doesn't cover. Asterisk code coverage analysis asterisk. Asterisk purpose asterisk measures how much of the target program's code is being executed during fuzzing. This helps you understand whether the fuzzer is exploring all the relevant code paths. Asterisk tools asterisk. Asterisk gov/lgov asterisk these tools are commonly used with GCC. You compile the program with coverage instrumentation, profile arcs FTIST coverage, and then run the program with various inputs. After the run, you use gov to generate coverage reports, and lgov to combine the reports into a single HTML-based report. Asterisk LLVM/LLVM prof data asterisk these are the LLVM equivalents of gov/lgov. They are used with Clang. Asterisk AFL has built-in code coverage instrumentation that is used to guide its mutation strategy. AFL favors inputs that explore new code paths. Asterisk benefits asterisk identifies areas of the code that are not being tested by the fuzzer, allowing you to improve the fuzzer's effectiveness. Example, compiling with address sanitizer, ASAN. If a buffer overflow occurs, ASAN will provide a detailed error report, including the type of overflow, the address involved, and the stack trace. 5. Dealing with complex input formats. Fuzzing applications that handle complex input formats, example network protocols, image files, video files, documents, is more challenging than fuzzing simple command line utilities. Asterisk grammar-based fuzzing asterisk. Asterisk concept asterisk instead of generating random bytes, grammar-based fuzzers generate inputs that conform to a specific grammar. This ensures that the input is mostly valid, increasing the likelihood that the target application will process it and potentially trigger vulnerabilities. Asterisk tools asterisk. Asterisk AFL Smart asterisk an AFL modification that supports grammar-based fuzzing using a context-free grammar. Asterisk Peach Fuzzer asterisk a powerful fuzzing framework that allows you to define complex data models and grammars. Asterisk libfuzzer structure-aware fuzzing asterisk libfuzzer can be used with a defined data structure to guide mutations. Asterisk example asterisk fuzzing a PNG image parser. You would define a grammar for the PNG file format, specifying the structure of the PNG header, chunks, and data. The fuzzer would then generate PNG files that conform to this grammar, but with deliberate corruptions at various points. Asterisk structure-aware fuzzing asterisk. Asterisk concept asterisk the fuzzer understands the internal structure of the input data. It can then make more intelligent mutations based on this understanding. Asterisk techniques asterisk. Asterisk data mutators asterisk instead of randomly flipping bits, data mutators operate on higher level data structures. For example, a data mutator might change the width or height of an image, or modify a field in a network packet. Asterisk data validation asterisk check the mutated data against format constraints to ensure it is still valid, to a certain extent. Example, grammar-based fuzzing with AFL Smart asterisk. This requires installing AFL Smart. 1. Define a grammar asterisk create a grammar file, example png.grammar, that describes the PNG file format. This is a complex task, requiring in-depth knowledge of the PNG standard. See resources online for examples. 2. Run AFL Smart asterisk. 6. Advanced fuzzing strategies. Asterisk feedback-driven fuzzing, coverage-guided fuzzing. Asterisk concept asterisk the fuzzer uses feedback from the target program, example code coverage information, to guide its mutation strategy. Inputs that explore new code paths are favored. Asterisk tools asterisk AFL, libfuzzer. Asterisk example asterisk AFL uses code coverage to determine which inputs lead to the execution of new basic blocks in the target program. It then prioritizes these inputs for further mutation. Asterisk hybrid fuzzing asterisk. Asterisk concept asterisk combines different fuzzing techniques to leverage their strengths. For example, you might combine mutation-based fuzzing with generation-based fuzzing. Asterisk example asterisk you could use a generation-based fuzzer to create a mostly valid input file, and then use a mutation-based fuzzer to introduce small random changes to the file. Asterisk differential fuzzing asterisk. Asterisk concept asterisk feed the same input to multiple implementations of the same functionality, example different image decoders, and compare their outputs. Discrepancies in the outputs can indicate vulnerabilities in one or more of the implementations. Asterisk use case asterisk useful for finding bugs in libraries or systems with redundant implementations. Important fuzzing considerations asterisk. Asterisk resource allocation asterisk fuzzing can be resource intensive. Allocate sufficient CPU cores, memory, and disk space to the fuzzer. Asterisk fuzzing time asterisk fuzzing can take a long time to find vulnerabilities. Run the fuzzer for extended periods, days or weeks, to increase the chances of discovering bugs. Asterisk reproducibility asterisk ensure that you can reproduce the crashes that the fuzzer finds. This is essential for debugging and fixing the vulnerabilities. Asterisk prioritization asterisk not all vulnerabilities are created equal. Prioritize fixing vulnerabilities that have the highest severity and impact. Heap overflows, remote code execution, and privilege escalation vulnerabilities are generally the most critical. Asterisk regular fuzzing asterisk incorporate fuzzing into your software development lifecycle. Regular fuzzing can help you find vulnerabilities early, before they make it into production. Conclusion asterisk. Fuzzing is a powerful technique for finding buffer overflows and other vulnerabilities. By understanding the fundamentals of fuzzing, crafting targeted fuzzers, analyzing crash dumps, and using instrumentation techniques, you can significantly improve the security of your software. Remember that fuzzing is an ongoing process, and it's important to fuzz regularly to keep your software secure. This tutorial provided more advanced techniques that can be used on top of the content of the 3 prior episodes. Good luck.